Okay, I'm going to wrap up my Chapter 2 College Algebra lecture series on a section I'm labeling 2.8, Rational Functions. Now, rational functions may or may not be covered in a course you're taking in College Algebra, and if they are covered, it varies on the extent to which an instructor will cover it as far as the depth that they'll go with rational functions. If you have to take a pre-calculus course or a business calculus course or a Cal 1 course, you'll certainly have to deal with these rational functions. So the first thing let's talk about is a definition of rational functions. Now this is a simple definition. Basically, a rational function is a function that can be written as the quotient of two polynomials. And so here you have some examples. 1 over x is one of the simplest forms of rational functions. Technically, a constant is a polynomial with degree 0. And of course, x is a polynomial with degree 1. This next one on top you have, in the numerator you have a quadratic function, and in the denominator you have a cubic function. So this is a polynomial over a polynomial. And then over here you have in the numerator a linear function, and in the denominator you have a quadratic function. So all of these represent rational functions. Now, can you find the domain of these rational functions? Well, we've covered this extensively, so I won't spend a lot of time on it. Basically, 1 over x just cannot be 0 because you can't divide by 0. So x can't be 0, and the interval notation would be negative infinity to 0, parentheses, union, parentheses, 0 to infinity. Now, this one here, this actually will factor, and I'm going to factor it for you. So if you factor the top, you basically will get x minus 1 times x minus 1, and I just wrote that as x minus 1 quantity squared. If you factor the bottom, you're going to get x minus 2. This is difference of cubes, and you can factor it into x minus 2 times x squared plus 2x plus 4. Almost ran out of room there, so hopefully you can see that. I'll read it again. This is x minus 2 times the quantity x squared plus 2x plus 4. Now, this will not factor further, and the reason is the roots to this quadratic equation on the bottom are non-real solutions. So there's no real, if you set this equal to 0 and solved it, you would get no real solutions. But if you set x minus 2 equal to 0, then you would get x equal 2. So the only number that x cannot equal in this function is x equal 2. Now, you know, some students would say, well, what about x equal 1? Well, if x is 1, that will make the numerator 0, and it's okay to have 0 in the numerator as long as you don't have 0 in the denominator. So x equal 1, that would not be a problem. That's not an issue. The only issue is x equal 2. So x cannot be 2, so the interval notation would be negative infinity to 2, union 2 to infinity. That would be the domain. Okay, I wanted this to be 25 here and not 5. I know up here I used a 5, but actually I wanted this to be 25 here, because what I want to do on this one is show you that if you factor the denominator here, x squared minus 25, well, it actually factors into x minus 5 and x plus 5. So I wanted to give you an example of a problem where you have two values that must be excluded from the domain. And I figured it was easier to do 25 than, I mean, it would have worked if I'd have kept it at 5, but then you would have had square roots to deal with. So this is just x squared minus 25. So factors in x minus 5, x plus 5, and of course if x is 5, then this would be 0, so that would cause us problems in the domain. And if x is negative 5, this factor would be 0, and that would cause us problems in the domain. So x cannot equal plus or minus 5. So that means the interval notation would be negative infinity to negative 5, union negative 5 to 5, and should be a parentheses there, and then union 5 to infinity. So basically, it's all real numbers excluding negative 5 and 5. And that's the... Okay, let's talk about finding the intercepts of these rational functions. We've done a little bit of this in the past. This rational function, if you were to set it equal to 0, the only way a fraction can be 0 is if the denominator is, the only way a fraction can be 0 is if the numerator is 0 and the denominator is not 0. Well, the numerator is 1, and since 1, there's no way that 1 can be 0, then you're not going to get, there's no way that y can be 0, in other words. So if y can't be 0, then you're not going to get an x-intercept, okay? And also here, x can't be 0, because if x was 0, then you would be dividing by 0, which is undefined. So if x can't be 0, there's no y-intercept. So for this particular graph, you're not going to get any intercepts. And you can graph this and see if you want to, but I'm not going to graph right now. Okay, now this one, if you were to let x be 0, remember how to get your y-intercept, you let x be 0. So basically what would happen is all of these terms right here would disappear because they would all be 0. And you would get 1 on top and negative 8 on bottom, or 1 over negative 8. So that would give you negative 1/8 for the y value. So the y-intercept is negative 1/8. Now let me refer to the factored form up here. If you wanted to set the y values equal to 0 to get the x-intercept, basically you would be saying, when is this expression equal 0? Well, again, the only way this fraction can be 0 is if the numerator is 0. And remember up here, the numerator can actually be written as x minus 1 quantity squared. And the only way x minus 1 quantity squared can be 0 is if x equals 1. So 1 would be the x-intercept. Okay, and then this other one here, again, if you let x be 0, and notice I changed it to 25 here as well. If you let x be 0, those two terms would disappear, and I know I wanted this to be over negative x squared minus 25, so I don't know why I didn't change it in all these places. But anyway, here we go. Okay, so if you let x be 0, then these two will disappear, and you'll get minus 3 here over minus 25. And of course, a minus over a minus is a plus. So your y-intercept would be the point 0 and 3/25. So that would be your y-intercept, 0 and 3/25. Okay? All right. So then, if you want to get the x-intercepts, what you have to do is figure out what's going to make this equal 0. So you would have to set 2x minus 3 equal to 0, and then you would just solve that equation, and so 2x would be 3, and then you would divide by 2, and x would be 3/2. So the x-intercept would be 3/2, which corresponds to the point 3/2, 0. Okay, so that's how you find the x and y intercepts of rational functions. Let me go ahead and I want to show you one that can be a little tricky for some students. So just bear with me here. I want to show you one. Okay, so for now, just ignore the heading here that talks about asymptotes, and let's just look at this for just a minute. If you were to factor the top of this, it would factor as x plus 1 and x minus 1. And then if you factor the bottom, you could factor an x out, and it would factor into x minus 1. Okay, so if you wanted to find the intercepts, well, first of all, you can't get a y-intercept because if you let x be 0, you're going to get negative 1 on top, but you're going to get 0 on the bottom because, 0 squared minus 0 is 0. So there's no y-intercept because x can't be 0. But what about y? Is there a way y could be 0? So is there any way this expression could be 0? Well, what a lot of students would do is they would look at this and they would say, okay, well, if x plus 1 is 0, then that's going to equal 0, right? So you're going to get negative 1 as one of your x-intercepts. And then they would say, okay, what makes x minus 1 equal to 0? And then you're going to get x equal 1, okay? But in actuality, x equal 1 is not an x-intercept because you have a common factor of x minus 1 in the top and the bottom. So if x was 1, you would actually get 0 over 0, which is undefined. And so the only x-intercept you're really going to get here is x equals negative 1. And I'm going to show you the graph of this one so that you can actually see what's really going on. So here's what the graph looks like. Notice, it has what we call a vertical asymptote here at the origin. Okay, but here's the deal. Obviously, you can see that it crosses the x-axis at negative 1, 0. So it definitely does have an x-intercept at negative 1, 0. And it doesn't cross the y-axis, so therefore, it corresponds to, that confirms what we found. It has no y-intercept. But what about that point, positive 1, 0? Let's see, was it positive 1, 0? Yeah, positive 1. Well, let's just say x equal 1. Okay, so at x equals 1, remember you don't get 0, right? You don't get 0 because if you plug x equal 1 in, you actually get the top 0 and the bottom 0. Okay? All right, let's take that away for just a minute. Now, notice what happens as I get close to 1. All right, look. You see that? See that hole? See, this particular graph has a hole at x equal 1. And that's generally what happens when you have a common factor in the numerator and denominator. Most of the time, the values where you have that makes that common factor equal 0 will give you a hole in the graph. Now, we can't talk about the y value. You see the y value of that hole is 2, but we couldn't really go into more detail about this unless we talked about limits. And you can't talk about limits unless you get into calculus. So anyway, let's just suffice it to say that obviously x equal 1 is not an x-intercept here because obviously it does not cross the x-axis at x equal 1. But you do have an x-intercept here at negative 1. Okay, so that's just a little bit of a tricky one that you might run into when you're looking for x and y intercepts. And I'll go ahead and shut this video down. In the next video we'll talk about asymptotes.